Welcome, everybody. I'd like to welcome you to tonight's O'Hara Lecture in Philosophy of Physics. We're really delighted to have Eleanor Knox here to join us from King's College London as our speaker tonight. My name is Ben Feinsteig. I'm a faculty member in the philosophy department, and I just want to begin with a few remarks about this lecture series as a whole before I'll hand it off to my colleague Josh Eisenthal to introduce our speaker. Okay, so some of you, maybe before coming here, had never heard of philosophy of physics. You might be wondering, why is the philosophy department hosting a talk about space and time? Well, here at the University of Washington, our philosophy department prides itself in what we think of at least as our unique brand of engaged philosophy. In a variety of ways, we're interested in how philosophy can be applied to the real world and how philosophical reasoning can aid in any number of applications. So, for example, we grapple with questions like, what do we owe to future generations concerning our environmental impacts? Or what are the ethical implications of neural technologies? And we also have a research cluster of folks doing what's called philosophy of science, folks who think about the status of our scientific knowledge and the interpretation of our best scientific theories. So our O'Hara Lecture Series takes up philosophical issues in the context of kind of the forefront of physics, with the aim of making these topics accessible to a public audience, as well as motivating the kind of work that we do. This lecture series is made possible through generous donations from Patrick O'Hara and Katarina Randolph, and we express our deep gratitude for their continued support. Past iterations of this lecture series have covered topics from the arrow of time in physics to naturalness in particle physics, and even the status of cosmology as a science. So continuing in this tradition, tonight, Professor Knox will be telling us about the role of space-time in the context of modern physics. A quick logistical note, after Professor Knox's lecture, which will be about an hour, we'll then have a question and answer session here for about 30 minutes. Afterwards, we'll invite you to a reception upstairs in the Walker Ames room. That's 225, but hopefully you'll be following. People will all be funneling up there. We'll have food, drink, and more philosophical conversation. Okay, without further ado, I now want to hand it over to my colleague, Josh Eisenthal, who will be giving our speaker a more thorough introduction.
Hi. So it's a real honor to have Professor Knox visit us, who's flown all the way from England to be here for this talk. And I know what that flight is like, so thank you. She's been doing this particular field, the philosophy of physics, all the way back to her undergraduate. This quite unique course at the University of Oxford that really integrates the two fields, physics and philosophy. In some sense, I followed in her footsteps because that's also how I got interested in the philosophy of physics, ending up doing philosophy and physics in this particular combined degree. When I started it, I didn't really know what philosophy was because we didn't get a chance to study that in school, and then realized that my interest in physics was really a kind of interest in philosophy, these foundational questions about what the world is and how we know about it. Professor Knox has followed this fairly time-worn tradition of staying at Oxford for a while, doing undergraduate degree there, then a master's degree there, then a PhD there. I mean, if it isn't broken, don't fix it kind of thing. She did, however, then manage to leave Oxford, which some people don't do, I can tell you. She did a Chandaria research, she was a Chandaria Research Fellow, am I saying that right? At the University of London. She was also a Leverhulme Early Career Fellow at King's College London. These are both prestigious early fellowships. In fact, she's still at King's College to this day. She also spent time visiting the US and also Canada. She was a visiting fellow at the Perimeter Institute for Theoretical Physics, which I think really shows how closely integrated philosophy and physics can be in some people's work. And she was also a visiting assistant professor at the Department of History and Philosophy of Science at the University of Pittsburgh. In fact, that's where I met Eleanor for the first time. She was teaching a graduate seminar on space and time. and this was one of my first graduate seminars in this field. I don't know if you remember, I said something very nerdy about this class. I said something like, do you remember this? Okay. I said something like, oh, this weekly meeting we have is one of my favorite intervals of space and time in the week, something like this. And she did not let me get away with it. She really was like, wow. And I remember that to this day, but it's fine. She's a decorated scholar, and she's done amazing work going back now for a long time. And she also won the Cushing Memorial Prize in Philosophy of Physics for an early paper that might feel a long time ago now. But more relevant for today, what she'll be telling us about space-time functionalism, this has actually launched an entire sub-literature in the field. And I think it's not an exaggeration to say that Eleanor played no small part in kicking that off. So, without further ado, please join me in welcoming our speaker for today.
Does that need to be blue? Oh, is it on? Can everyone hear me? Yes, okay, wonderful, sorry. Fantastic. Well, thank you very much for inviting me for that lovely introduction. I think a lot of people have made really nerdy jokes in my classes, including me, but they're not all seared in my memory. It struck me also that introduction was, a history of how relatively inertial I've been in moving institution. And, another lesson from this talk could be that inertia is very important. So there's a nice tie-up there. Anyway, so massive thanks for inviting me. I think it's just amazing that this exists. I actually think philosophy of physics is a wonderful way to publicly communicate physics. I'm thinking about turning this mic down. Someone tell me if it sounds like it's feeding back a bit. Tell me if you can't hear me, though. So I think philosophy of physics is a brilliant way to communicate physics in general. This is going to be a proper philosophy of physics talk. But I often think that the questions in physics that really excite people, that really get them motivated to study the subject, are in fact these really frustrating questions that you're not always allowed to research in the physics department. And the beautiful thing about a philosophy department is you're allowed to think about the mind-bending bits of physics, in a sense in the absence of application, and that's often just very exciting. So I think that it works really well if you're trying to explain what's exciting about physics, to take a little look at the philosophy of physics. All right, so what I'm going to be trying to do today is persuade you that there's a particular kind of view of philosophy of space and time, or of the physics of space and time, or of what space-time really is, that we need to have to accommodate what you might think is going to happen in 21st century physics, or perhaps, in a sense, what we hope might happen in 21st century physics. And I'm going to try and persuade you that there's an old view of space-time that is very appealing, but that isn't really tenable anymore. Now, the trouble with taking an audience and trying to persuade them the old view isn't tenable is I have to kind of get you clear on what the old view is before I can persuade you should dismantle it. So the first bit of this talk is going to be dedicated to some extent to trying to tap into the intuition that I'm trying to dismantle, and then I'll go about telling you why you shouldn't have that intuition in the first place. So let's get started on that. So we'll start with space. Let's not worry about space-time for a couple of minutes. Let's just start with the notion of space. What do you think about when you think about space? And I mean, in a sense, I don't mean kind of, outer space or some stars, although it could be that. I mean space in this really big, abstract sense. The space that everything lives in. The space that matter is defined within. The space that might perhaps be infinite. I think there's a very deeply ingrained way of thinking about that space, and I think it goes all the way back. It goes back at least to Democritus and the atomists in the 5th century BC. There's an argument it goes back further than that even, that it's around in kind of folk theories in really ancient Greece. And it's that space is some kind of stage, arena, container in which we all live. It's a very natural way to think about it. It's a thing kind of in its own right, perhaps, and it is the background or container for everything else, for matter. It's quite a deeply ingrained notion. It was Newton's notion. Fast forwarding, the history will be rapid and potted in this talk. So we're going to quickly fast forward 2,000 years to Newton. Newton had this notion of space. So the atomists thought there were atoms in the void, and the void was kind of a thing. Newton thinks that absolute space in its own nature, without relation to anything external, remains always similar and immovable. He thought absolute space was the thing with respect to which positions and motion of bodies were defined. It could exist without bodies. It was independent of them in a certain sense, and it provided a background for them. So it was a kind of box or container for matter, is the thought about absolute space. Now, I'm going to be gradually kind of problematizing container spaces, and the problems start early. The problems famously start when Leibniz starts worrying about Newton's notion of space, and Descartes has views on this too. There's plenty of countervailing views to this kind of container notion of space around. But I think it's helpful to think a little bit about the limitations, even at this level, even in the context of Newtonian physics, and even in the context of just space and not space-time, about the limitations of thinking of space as a container. When you think of a container, you often, I think about two things implicitly. You think about a kind of box with edges, and you might think about a preferred coordinate system. What do I mean by preferred coordinate system? Well, if you look, the previous slide. Oh, I want to go to the previous slide. Oh, never mind. There we go. Previous slide had a kind of grid on it. That was a kind of Cartesian coordinate system, right? The x, y, and z coordinates you're probably familiar with from having been sort of forced to draw them out at some point in your education. I think we implicitly often kind of imbue these notions of container spaces with the idea that things have a position, perhaps a position that's kind of labeled by some kind of preferred coordinates, and that there's some kind of position relative to kind of the edges of a box. And of course, neither of those things look to be true about space. Space doesn't have preferred coordinates, even for Newton in absolute space. And it doesn't also, for Newton and the atomists at least, didn't have edges. It was proposed to be infinite. So thinking about positions in infinite space is already a little bit tricksy. Leibniz pointed this out to some extent. He said, look, one of the problems with your notion of absolute space, Newton, is that everything's got a position in absolute space, but if you pick everything up and hoik it 3 feet to the left, it doesn't make a blindest bit of difference. Nor does it make any difference if you give everything a velocity of 300,000 miles per hour that was once at rest. The physics doesn't care. We'd never notice, and we could never know whether things really were at rest or they were moving at 300,000 miles per hour. I don't think Leibniz says 300,000 miles per hour, but that's the general idea. So these are famously the Leibniz shifts. Leibniz is using them to argue against a view called substantivalism, which was Newton's view that space was a substance, and Leibniz thought that space was a network of relations amongst bodies, relationism. But they have a relation to some of the problems that we'll talk about today, which is that once you actually start pushing on these notions of absolute space or container, sometimes you discover that the notions are a little bit more slippery than you think they are. Now, when you do a standard philosophy of physics course, if there is such a thing, there is in a few places, one of the things that you'll get taught pretty fast is that the solution to, in particular, this problem with motion, this problem that you wouldn't be able to tell if this lecture room was sitting at rest or it was moving at 300,000 miles an hour. Trust me, you wouldn't be able to tell. One of the solutions to that is to move with a particularly big historical and Whiggish leap to space-time. So now we fast forward to 1908 and Hermann Minkowski, who takes a theory developed by Einstein, special relativity, but a theory that's written in terms of coordinate transformations. It's a theory that tells you about how to take something in one set of coordinates or reference frame and describe it in another, with some very surprising consequences. He takes it and he casts it into this four-dimensional form, this space-time form. So this is the advent of the notion of space-time rather than space and time. And he says, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only kind of union of the two will preserve an independent reality. So now the thought is that we can think of not space and time separately, but space-time as the four-dimensional container in which everything lives. Minkowski's not talk about containers. I'm kind of putting that word in his mouth. But a natural way to think about Minkowski space-time is as this analogous to space in previous theories, background or container that everything lives in. And it solves this problem of motion because space-time itself doesn't have a standard of absolute rest. It just has a standard of straight lines, which are constant velocity lines, and curved lines, which are accelerating lines. And it doesn't naturally need to have a matter of fact about what's the same place at different times once you move to this four-dimensional kind of block view of the universe. That's been enormously influential. Given that some of the point of this lecture is going to be to slightly reel back on that, it's relevant that Einstein was a bit of a curmudgeon about the notion of space-time. He called Minkowski's recasting of his theory into four-dimensional form superfluid learnedness. I should have remembered the German, because I think it can be translated in various kinds of ways. But that was his thought. He said, oh, you know, this is just a cute mathematical trick. All the physics is actually in these coordinate transformations I gave you that tell you what to do with the laws and the stuff that goes in the space-time. Perhaps, unfortunately for Einstein, certainly meant he had to go and learn a whole load of maths. It turned out that Minkowski's formulation was quite important to solve the next problem he worked on, which was the problem of gravity. So Einstein eventually had to get on board with this four-dimensional space-time notion, because in order to incorporate gravity into his theory, he eventually needed to move to what we now think of as a curved space-time theory, that is general relativity. So general relativity is our best theory of gravity. It tells you that matter moves the way it does because of the curvature of space-time, and space-time curves the way it does because of matter. We often teach people about it using this kind of rubber sheet analogy over here, where you picture a big two-dimensional surface of a rubber sheet, and you stick a massive body in it, and you distort the geometry of that surface. And you therefore distort the natural paths on that surface. The rubber sheet analogy is really useful. I think most people have to use some version of curved two-dimensional surfaces if they want to explain what they mean by general relativity to an audience. But again, I'm going to be in the business of dismantling metaphors, so I'd note that this has some fairly major limitations. I mean, whenever you see the rubber sheet analogy, I mean, there's a kind of irony in the fact that you put a massive body in and it's gravity that pulls the massive body down. And also, presumably, if something's moving on the surface of that rubber sheet, something needs to hold it to the surface such that it follows those trajectories. It's not quite clear that the analogy can do all the work that we usually think it does. But nonetheless, enormously successful theory geometrizes gravity, makes gravity an aspect of space-time curvature. And to stay close enough that I can actually click this thing. Okay. All right. So then, I told you we were on a whistle-stop tour of physics, gone from the atomists. Now we're up to the kind of middle of the 20th century. People start thinking, well, look, if Einstein was so successful in geometrizing gravity as a force, why don't we try that with some other forces? So people think, well, look, thinking of space-time and space-time geometry as having more dimensions, that's going to be really successful. So one of the first theories that does this is a theory called Kaluza-Klein theory, which tries to take electromagnetism and wrap it up into geometry. And then eventually, a little later, string theory, or contemporary string theory, says things that like space-time has 10 or 11 dimensions, depending what string theory you're doing. And its explanation, which is the same as the Kaluza-Klein explanation for why we don't notice the extra 6 or 7 dimensions, so we see ourselves as living in a four-dimensional space-time, 3 dimensions of space, 1 of time. The reason we're meant not to notice those is because something called compactification. So the analogy that's usually used for that is what's sometimes called the garden hose analogy. Picture taking a two-dimensional surface and you wrap it up into like a long tube. Zoom out, you see it as a one-dimensional thing, and the compactification is meant to be a bit like that. So the kind of standard popular presentation of string theory would say, oh, string theory postulates a higher dimensional space-time, but some of the space-time dimensions are compactified. And you get pretty images like this one. This is meant to be a Calabi-Yau manifold, so the idea is that every point in space-time, you've got a little crinkled up set of maybe 6 or 7 dimensions. I think it has to be 6. In this particular case, you need an even number of dimensions to do this. And the images get very pretty, and we're very visual people, right? I think there's quite a lot in this little history and the sway that it holds over us in the fact that humans are very visual, and we like to be able to imagine things visually. I've attempted to put an image on every slide today because you're all visual people. But sometimes the visuals can lead us astray, because of course one of the problems when we're talking, I mean, even if you take the space-time business very seriously, one of the problems here is that we're talking now about 10-dimensional spacetimes, and I've just given you a 2-dimensional drawing. I mean, its limitations are going to be obvious. Just as in the rubber sheet analogy case, some of these visuals need to be sort of kept within the context that they're appropriate in. And I think you would be forgiven, and in fact you'd be on the right track, if you were a little bit concerned that some of the claims that are made by string theorists, and I should modulate a bit, because of course the claims that people make when they're popularizing theory and how seriously and what they think about the actual mathematics that they're trying to write down are often a little bit different. But you'd be forgiven if you sort of started to think, well, is there some sense in which we don't really know whether this is anything to do with space-time at all? There's some really complicated maths here with some very high-dimensional spaces. But the claim that it's thus a space-time theory is kind of layering perhaps a layer of metaphysics on that you might think isn't entirely appropriate. So I think you should, at this point, ask what that all really means to claim that space-time, say, has 10 dimensions. I'm not saying it doesn't mean anything. I'm just saying that one should ask, what's the content of that claim? I can define plenty of higher dimensional spacetimes. Mathematicians can define even more. Geometry is this brilliant, flexible tool. Configuration spaces in quantum mechanics have 3 times the number of particles as their dimensionality, right? And if you think that Avogadro's constant has 26 zeros, that's just an awful lot of dimensions in a space that we're using to describe any system. That's the kind of thing you play with in maths and physics. But it doesn't mean you have to take all of those things seriously as kind of physical space, right? Most of those aren't supposed to be space-time. So I think a question you could ask yourself is, when a string theorist, if they choose to, says that space-time has 10 dimensions, are they just saying, I've written down a mathematical theory in 10 dimensions, or are they making a more substantive claim than that? And if the latter, what's the content of that claim? Just to hammer home the fact that not all spaces are space-time, consider color space. So color space is a space that you can use to describe colors as presented on a computer screen, for example. This is a very, very simple 3-dimensional color space with a red, blue, green axis, and every point in the space describes some combination of 3 colors. It's super useful. You can define color spaces with interesting geometries. But you haven't thereby said anything about space-time. It's just rather obvious that what you're doing is representing colors, not representing anything about physical space. So no one thinks that space is space-time. So there's presumably some difference between a theory that makes a claim about space-time and a theory that makes a claim about a mathematical space. How do we locate that difference, and what's it supposed to be? Well, one obvious thing you think, and that I've intuition pumped you hopefully to think a bit, is, well, you kind of know from the beginning of this talk what that claim is meant to be. One is a claim about some abstract mathematical space, and the other is a claim about this thing that we live in, space-time. Now, one traditional way of thinking about that is that there is a fundamental space-time. We kind of know that, however we come to know it. And that we might have different theories about it, we might be right or wrong about it, but we succeed in talking about it even when we get some features of it wrong. Because there is, in existence, a fundamental thing, space-time. And it's the fundamental container arena. That metaphor is helping you refer to it, helping you get a handle on it. But I think you could question that. I think you push hard on the idea that space is a stage or container or a metaphor. You realize that a lot of that idea is extrapolated from, example, the way I feel about the space in this room. But the way that I experience the space in this room, of course, is as a bounded space with a sense of rest, a sense of motion, preferred coordinates, lots of things that an infinite space-time absolutely doesn't have. I mean, regardless of what you think about space itself, space-time is a very different beast. There's no way to pick out the same place over time. If you start to look at some of the content of the container metaphor, you might start to worry about exactly what it's doing. You might be able to say some things about the container spacetime. Perhaps you take it that you need a spacetime to write down the rest of your equations of physics or something. But those are going to be slightly different notions from that intuitive metaphysical notion of container that we started with. And one reason why you might end up slightly forced to really abandon your container metaphor is that you might think that if we're not to be too bossy from the philosophy department, that we need to accommodate a notion coming out of physics, which is a notion of emergent spacetime. Now, there's always a bit of a funny thing when you try and philosophize about what's called quantum gravity, right? Because quantum gravity doesn't exist. We don't have a theory of quantum gravity. We have candidate theories of quantum gravity, but we don't have a theory of it. It's a theory that if it existed, would manage to explain how gravitation can fit into quantum theory. So there's all kinds of ways it might do that, but presumably the most natural way to think of it is it provides some kind of underlying theory from which both quantum mechanics and general relativity, our best theory of gravity, can be derived or emerge. There are different camps in quantum gravity, and they don't always agree. But quite a few people in both camps think that a lesson of their respective theory, or both camps, there are many more than two camps, think a lesson of their theory is that space-time, at the very least the space-time of general relativity, but perhaps space-time in general, is going to be non-fundamental. They say it's going to be emergent. Happy to talk a little bit about what I mean by emergent here. But they think it's going to be something that kind of comes out in a higher level of theory and isn't there in the most basic theory. Now, if your notion of container that was kind of doing that work that you took yourself to be referring to was a notion of a kind of fundamental thing in which everything lived, emergent space-time is a bit of a contradiction, right? Because what we're moving away from if we move to a theory that doesn't appear to have space-time at the fundamental level, I'll say a tiny bit about how that might look in a theory a little bit later on. If we move away from the notion, so a very natural way to think about moving kind of down the levels of fundamentality is there is space-time, and you kind of zoom in and you get to a smaller scale of space-time, and you get closer and closer to the fundamental particles. But the space-time itself sits there in the background as the home for everything all the way through this process. If space-time itself is emergent, you have to give up on that idea. If we give up on the container metaphor, which I think was questionable anyway, then we need a way to understand the difference between a claim about space-time on the one hand and a claim about abstract mathematical spaces on the other. Because one of the things, if we're going to have emergent space-times that we need, is we would need to be able to find space-time in our higher level theories. So I'll talk about some examples later, like temperature. Like one of the things you need to understand, if you don't think temperature is there in absolutely fundamental physics, if you don't think that, at the very, very base level, sort of temperature is one of the properties, you can think some kind of aggregate emergent property, you need to know what a temperature is such that you can recognize it when you come across it. So we need a way to identify space-time in our emergent theories. Now, it might be obvious why this wouldn't be a goer, but there's a thing that's tempting, I think. It's not intuitive in the way that the container space is, but it's tempting if you've steeped yourself deep in the mathematical tools that we use to describe general relativity. It's tempting to kind of think that we do have a handle on space-time because we know how to mathematically describe it. So if you do a whole bunch of general relativity courses and some differential geometry, you'll learn that you represent a space-time by laying down a four-dimensional manifold and then a particular kind of pseudo-Riemannian metric with an associated derivative operator, various kinds of mathematical geometrical object to represent a space-time. And you certainly, within the philosophy community, get some people who say, well, when I say that I postulate a space-time, that's just what I mean. I just mean I wrote down this mathematics. So you might think that actually this question of how do you find space-time in your theory gets kind of answered by the mathematical form of your theory. You just look for the appropriate mathematical stuff, and that's how the theory describes space-time. But of course, that's going to hugely constrain future theorizing and have lots of counterexamples. There's absolutely no reason you can't use pseudo-Riemannian geometry to describe something that's not space-time, and there are plenty of theories already, and there could be plenty of future theories that don't use anything like the general relativistic tools to describe space-time. So it doesn't look like mathematics is going to come to your rescue if you get rid of the container metaphor. Now, here's a thought that you might have. The container metaphor had within it, at the very least, one feature, which wasn't really mentioned. It sort of talks about stage or arena, but the point was that the idea behind the stage or arena was that it had some kind of relationship to the behavior of stuff. And things can only be a space-time if they have the right kind of relationship to the behavior of certain kinds of stuff. I think that's going to be absolutely correct. But then you might ask, what kind of stuff? And you might think, well, what's the minimal thing that we could think? Well, space-time should relate to distances and times. That's like the space bit and the time bit. That's very important. So there are certain kinds of systems that measure distances. We're going to call those rods. You can call them something else if you like, or rulers. And there are certain kinds of systems that measure times. My wristwatch, less accurately, the biological process of aging in my body, more accurately an atomic clock. These are all periodic processes that manage to measure times. So you might think that one thing a space-time had better do is have the appropriate kind of relationship to the behavior of certain kinds of perhaps macroscopic system that we use for measurements. That's certainly true. It would seem very odd if you called something a space-time and it had no relation at any scale to anything that you might think of as a periodic process or a process that might have an associated distance at all. But you might worry it's not enough. Just getting out what we might call the operational or empirical significance of a space-time theory isn't all you want to do. You're making substantive postulates about the nature of a space-time. It needs to have a slightly richer role than that. The behavior of rods and clocks pins things down very much at the edges. It could be compatible potentially with more than one space-time, incompatible space-time structure. Moreover, if we're looking at theories of quantum gravity and wondering if they have space-times, the kinds of changes that we might be thinking of making to space-time structure might be such that big operational systems are left largely unchanged. You might have to think that they sort of somehow affect smaller systems, not directly measurable systems. You might have to come up with quite roundabout ways of measuring the effects of a theory of quantum gravity, even if it did distort the space-time in some sense. So this is where space-time functionalism, I've got halfway through the talk and I haven't even mentioned the core idea, space-time functionalism. This is where space-time functionalism comes in. I don't think I very often go 20 slides without saying those words, so you know, all my talks come back to the same thing. Space-time functionalism is a more subtle tool for taking that connection to matter that the operationalist wants, but pinning it down in a more thorough way. So the basic idea behind functionalism is to think, well, look, there's something right about operationalism in that you need to get kind of output behavior correct in your theory, but you also need to get the connections, the jigsaw puzzle correct, the connections to all of the other bits of your theory correct. Your space-time better be the right kind of gear in your gearbox, not just the thing that you ultimately output. And so what you want to do is you want to define some kind of theoretical role that space-time plays, which connects space-time to other bits of theory, like, say, matter fields. And then you just say that what the functionalist says is anything that plays that role in your theory just is space-time. So the functionalist commitment is that once you've specified that full role, there isn't anything additional to specify, like that it's also really the fundamental container, where you cash out fundamental container in some way that's not just about a theoretical role. So the slogan is space-time is as space-time does. That was Chris Woutrick and Vincent Lamb. But the idea is just that's it. Like, once I've told you what space-time does, and I've told you some piece of structure does that thing, I've told you it's a space-time. You can't have a further debate about whether it kind of fits into the metaphysical category properly. Now, I'm not sure whether it's fortunate or unfortunate, and perhaps unfortunate, but functionalism, the idea, is fundamentally borrowed from the philosophy of mind. And there's a sort of irony to this, because functionalism is probably at its most controversial in the philosophy of mind. I think it should be incredibly uncontroversial in scientific contexts, but is quite controversial in philosophy of mind. But if you've ever heard the word functionalism, it's likely to be where you've heard it. And the philosophy of mind functionalist is answering a question not unlike the question that I asked about operationalism. They're asking a question that says something like, look, suppose you want to be a physicalist about the mind. You don't think that there's a Cartesian dual mind to have mental states, but you want to understand how these lumps of grey matter in our heads can have things like beliefs and desires. A functionalist thinks that having something like a belief or a desire or a mental state is just to have a state that's picked out by its role in some particular, say, psychological theory. So if right now you're thinking, my God, it's 10 past 8, and when is this reception going to get started? I would really, really like a glass of wine. We're going to cash out the desire for a glass of wine as true just in case I or you are well described by some belief-desire psychology, where the desire for a glass of wine is playing. It's not just going to have the correct outputs, running for the bar at the end of the talk, but it's also going to have the correct kind of relationships to other bits of your psychology. It's going to be the correct kind of gear, fit in the puzzle correctly. Now, it's quite controversial. I think probably correct, but it's quite controversial to be a functionalist about philosophy of mind, because if you really are, hankering for a glass of wine right now, there's something that it's like to want a glass of wine. And if you think about a state like something like pain, a kind of purely qualitative state, it really feels like there's something that's like to be that. And there's a lot of worry over whether functionalism in the philosophy of mind can capture that what it's likeness. That's what's sometimes called qualia. But the great thing about scientific theoretical terms is they're nothing like mental states. They're not candidates for qualia, and we don't have this introspective, phenomenological access to them. They're just terms in our scientific theories. So functionalism should be far less controversial when it comes to scientific terms. Dan Dennett certainly believed this. He put it in the following kind of indomitable way. Functionalism is the idea that handsome is as handsome does, that matter only matters because of what matter can do. Functionalism in this broader sense is so ubiquitous in science, it's tantamount to a reigning presumption of all science. So that's Dennett saying we should just assume, in science you should effectively just assume you're a functionalist unless proven otherwise. I think that's very plausible when you look at various kinds of theoretical terms. So take the notion of gene, for example. Imagine you're some intrepid astrobiologist who's headed off to an alien planet, and you finally found life elsewhere in the universe. You found some self-replicating organism, microorganism. Perhaps its biology is really quite different from ours. Perhaps it doesn't have anything that that looks like the DNA double helix in it when you look at it. But it has other kinds of structures, and it seems to self-replicate. And you're writing a paper and you're having a debate about what we should attribute, whether it has genetic structure and how you think about genes. What's that debate going to be about? Well, it's ultimately going to be about whether some particular piece of structure in that organism plays a particular kind of role. So, for example, codes for a heritable characteristic. Perhaps codes for protein, perhaps you could be broader about the role. But insofar as you're going to try and work out what a gene is in this unfamiliar environment, it's going to be a discussion about what genes do, what their functional role is. And in more familiar contexts, if you actually just take a trawl through the medical or biological literature, you will indeed find that working scientists, when they talk about genes, are talking entirely about what genes do, their functional roles. Genes don't just code for proteins, some of them switch on and off other genes. We need to expand our concept of gene to allow a gene to be a bit of DNA that turns on and off another gene, not just code a protein. That's something that happened at some point in biology. I'm going to try and date that. But those are the debates that we have. And you don't have debates about exactly where to cut on the double helix on some kind of first principles view. You have a debate about what a gene is from the perspective of what it does within the slightly higher level genetics theory, not at the fine-grained level of the DNA double helix. Functionalism is also a pretty standard view, I take it, about something like heat or temperature. In this case, you've got a kind of contrast class because you've got kind of anti-functionalist view of heat with the caloric theory that was eventually disproven. The original thought was that heat was a fundamental substance. So heat just referred to that thing, right? Not something that played a role, but heat referred to this substance that flowed in and out of bodies, caloric. But when we came to know that there wasn't anything like caloric, we eventually came to understand heat transfer as energy transfer that's related to temperature change, and you think of temperature as defined by thermodynamic equations, for example, and various bits of thermodynamic theory, and heat gets picked out functionally by its relation to thermodynamic variables. So you start to think of heat and temperature not as things that you're referring to that are fundamental, but whatever it is that's creating, that's causing the thermometer to go up, but also that's playing a particular kind of role in your thermodynamic equations, counts as a temperature. One thing in particular, if you do something vaguely public-facing, I feel I ought to say, the quickest way to frustrate a lot of philosophers, but the most likely thing to happen if one ever talks to a science journalist about any idea like this, is that your piece will instantly get retitled, "Space-time is an illusion," which is not the point at all of functionalism. Functionalism is actually meant to be a way to secure the reality of higher order terms, right? To say that temperature or genes are functionally picked out by their role, not by being some kind of fundamental substance, is not to say that they are not real. I mean, poor old Joan of Arc. Temperature is very, very real for her in this picture, right? It's playing its role. It's not a nice one. So just to note that there's nothing about this functionalist picture that's meant to be eliminativist or claim that these higher level things are an illusion. It's intended to be a way of securing, if you think there's a kind of puzzle about how, if we think there's a fundamental layer and then some layers on top of it, how we secure the reality of the kind of terms that we use in higher level theories. And that's the role that functionalism is supposed to be playing here. Okay, so I think we should be functionalists about science until proven otherwise. Are there some kinds of terms in science that you shouldn't be functionalist about? And I think some people think yes. I think they think that maybe the fundamental things are kind of primitively given, for example. And so if you thought of space-time as a fundamental container, you might think it should be the exception to that general reigning presumption of all of science. But I think that a lot of that, first of all, is based on aspects of this container metaphor that kind of fall apart. There's this possibility being touted to us by the physics community that space-time might not be fundamental. And I think functionalism is rife elsewhere in science, and I would actually question that functionalism doesn't apply even to stuff as fundamental as you like. For example, I mean, I certainly want to be I'd like to be a functionalist about the notion of particle. I'd like to be a functionalist about the notion of force. I can't really think of a very good candidate for anything that I wouldn't want to be a functionalist about. So I think we should be functionalists about space-time. I don't think there's a good argument to carve out space-time and put it in a different category from other scientific terms. Okay. Now, most of the work in this kind of idea, and it's not, you'll be happy to know at this late hour, work I'm going to try and do with you now, is actually going to be in the nitty-gritty of picking apart space-time theories and looking at how they fit together and how these jigsaws work and what space-time really does in these theories. It's picking out the actual theoretical role for space-time. So it's only really going to be useful, this theory, insofar as we've done a bit of that work, which I've done elsewhere, but I'm not trying to do today. But here's a few things I'll say about it, just so you have a feel for what you're going to say about the space-time role. Space-time would better have some kind of relationship to distance and time measurements, whatever you take those to be in your theory. It should relate to natural or inertial motion. So one of the very big leaps that Einstein made when he came up with a curved space-time theory was to realize that freely falling bodies should be thought of as force-free bodies. So bodies falling under gravity really weren't subject to any forces, and that was the kind of huge leap that led to the curvature of space-time. The symmetries of space-time should relate in an appropriate way to the symmetries of the dynamics. That's a little bit more complicated, but that's related to this idea that I originally said, Einstein's first theory was about transforming things between coordinate systems. And that's a way of talking about the symmetries of, say, the equations of matter. And it turns out that whenever you have sort of universal symmetries of equations of matter of a certain kind, we tend to think they have to be hooked hooked up to space-time structure in a certain kind of way. And that's partly going to be essential to ensuring that space-time governs the behavior of matter in the right kind of way. As it happens, I think there's a kind of shortcut to kind of lots of these roles, which is this notion of the structure of an inertial frame. So an inertial frame is like a frame where the laws of physics take a kind of familiar form. If you've done a bit of physics, you might know that there's some reference frames in which physics is going to look nice and others where it's going to look like a bit of a nightmare and there are going to be illusory forces. The structure of the reference frames that are good to do physics in is going to be very closely tied up with these notions. But I don't need to argue in particular for that now. The point is that there are a very plausible, relatively rich set of roles for space-time that go a little bit beyond the operational. And once you define those roles, slightly unsurprisingly, they apply in general relativity, because that was one of our test cases of a space-time theory, so it'd be very odd if it didn't. That's where lots of these ideas come from. So the metric field of general relativity, this thing we sometimes call G mu nu, which represents the curvature, well, represents all of the geometrical aspects of space-time, including its curvature, so it defines distances and times and angles. It couples to matter fields in a way that relates its symmetries to the symmetries of matter in a very particular way. And related to that fact, you end up with the fact that the straightest possible lines of this metric field, this particular geometry, end up being the paths that freely falling bodies take. So in general relativity, you do have a thing that plays this space-time role. It's the metric. And so for the functionalist, the metric field just is space-time. It plays all the right roles. There is actually a debate about whether the metric in general relativity is really space-time or a gravitational field. And I think space-time functionalism closed down one half of that debate. It says, look, it's acting like space-time. It just is space-time. Whether it's also a gravitational field is another question. So good. So we've got something in general relativity. It plays all the right kinds of roles. General relativity has space-time in just the same way that, macro theories have temperature in them. There's something that plays all the right roles. There is a space-time. Now the question is, what about the underlying theory? What if general relativity isn't the last word and there's a theory of quantum gravity underneath it? Okay. So what is quantum gravity? I wish I knew. But here are a few things to say about it. We have a quantum theory of all of the forces except gravity. Various features of general relativity that are deeply tied up with the fact that it geometrized gravity instead of making it a force make it incredibly hard to quantize gravity. There are a couple of different routes to quantizing gravity, and both of them land you up in very deep problematic waters that you then have to use incredibly imaginative mathematics to solve that take you very, very far away from our familiar theorizing. So one of the traditional ways to think, there's more than two approaches to quantum gravity, but one kind of route takes you towards string theory and another route takes you towards a theory called loop quantum gravity. And to get a feel for why one might say that there's no space-time in these theories, let's have a little look at a single slide on loop quantum gravity. This is not going to be designed, obviously, to give you some deep sense of the mass of loop quantum gravity, but to give you a rough feel for the kind of thing loop quantum gravity theorists say. Loop quantum gravity, I think, has hit a little bit of a theory dead end. I don't think it's a terribly burgeoning research program, but it is an interesting example of a theory that looks like, that makes a reasonable claim to have nothing like space-time at the fundamental level. So loop quantum gravity quantizes the structures of general relativity through a kind of convoluted process and ends up with something they call spin networks. And we're meant to visualize spin networks like something like this, a bunch of nodes with some connections between them and some numbers on them. And these are called, these things are spin networks, the numbers are spins. That all kind of looks spatiotemporal, but then it does turn out in loop quantum gravity that these nodes and the numbers between them have nothing to do with locations. So two nodes being close to one another or having a small number connecting them doesn't tell you anything about them being hypothetically close together in space. That's not meant to be part of the theory. There are some, they're trying to get general relativity out, so there is a notion of area that you can get out that's related to the numbers of spins. But you get it out, because this is a quantum theory, by kind of layering these spin networks on top of each other. So you have superpositions of spin networks that fundamentally represent the world. So you can see in something like this picture that the claim that there isn't a fundamental space-time looks pretty plausible. Identifying something playing the space-time role in this kind of theory looks extremely difficult. I'm not saying that nobody could try, but it looks highly plausible that this is a fundamental theory that looks like it doesn't contain a familiar space-time. Okay. So, you've got general relativity, it does have space-time in it. Let's suppose you have a theory of quantum gravity with putatively no space-time, and you want to use functionalism to try and understand how that's possible, or kind of try and think about the connection between the two in some sense. There is a popular way in amongst philosophers of physics of trying to do this, but I don't think it works. So this is the bit where I'm going to suddenly reveal that functionalism means different things to different people. What I mean by functionalism is not what a very, very famous philosopher called David Lewis meant by functionalism. And Lewis has a really massive influence in the philosophy of physics community and the analytic metaphysics community in general. And so it's often what philosophers of physics would take me to mean by functionalism and what they would mean. So Lewis's notion of functionalism is very tidy. It's a tool for reducing one theory to another, for building these very tight connections between theories. And so if he was interested in being a functionalist about something like temperature, what he would say is, look, let's find the role that temperature plays in your thermodynamics, for example. And then you're going to define that T, that temperature, via its role in the theory. And then you'll look at some lower level theory. And for now, we'll talk about a toy theory to make this connection plausible. Let's talk about the kinetic theory of gases. That's like a very basic model of gases as kind of idealized little molecules moving around. You look in the lower level theory and you try and find a unique property that realizes that temperature role, that does the things that temperature do. And in the kinetic theory of gases, the realizer of that role is the mean kinetic energy of the molecules in the gas. That's the thing that plays the role of temperature. And so that thing just is temperature. There's an identity there. What you've actually done is you discovered this thing, T, was really mean kinetic energy of the particles all along. So you performed a kind of reduction of one theory to another. It's also part of Lewis's plan that if you couldn't find anything that played that role, what you've discovered is that temperature really didn't exist in the first place. You were just kind of wrong about temperature. All right. It's very neat and tidy. It does a very good job of securing the terms of your higher level theory by locating them in the lower level theory. So it gets rid of this worry that you don't have any non-fundamental stuff. Non-fundamental stuff turns out to really be fundamental stuff. Lots of virtues, it's a Lewisian picture. I just think truth is not among them, unfortunately. So the main problem with this picture is I think it's just wrong. It's not wrong philosophically, it's just wrong as a matter of fact about how our world fits together. So this is one of my big sticks. Temperature isn't mean kinetic energy, even though every philosopher seems to think it is. It's just not. The kinetic theory of gases is so far away from the full set of theories that we want to interpret a temperature to, like within, that it applies to an idealized gas of a very dilute ideal gas. I mean, but all these things in this room have a temperature. You know, you guys aren't ideal gases, and you all have a temperature. Temperatures are everywhere, not just in ideal gases. Temperature is just not mean kinetic energy. Temperature is, in fact, brought about in complicated ways as things that behave like temperatures very differently in different substances. And there isn't a sort of unique realizer property that we can just pinpoint in, say, at a molecular level. There are things we can say about temperature in statistical mechanics, but they're largely functional in nature. They're precisifying the notion of temperature. And I think what goes for temperature, I mean, actually one of our best examples of reduction is something like temperature. What goes for temperature goes even further for other kinds of examples, like, say, our theory of liquids and viscosities. If you actually start thinking about sets of equations that we understand quite well, we understand the terms in them pretty well, and we know how to apply them, and then you start asking, say, at the quantum level, what it is that so a discrete set of kind of quantum particles, what it is that realizes the property of, say, viscosity in a liquid, you're not going to find a property that you can identify with the viscosity of a liquid, a realizer in the Lewisian sense. You're going to find a story about how it's possible for a quantum system to be a liquid, but that story isn't going to go via what we'd call a type-type identification of properties across the two theories. So the trouble with reductive functionalism, this Lewisian functionalism, is it's false. And even when it's true, it leads directly to quite a strong form of reduction, not emergence. And that's a problem if you want to use it to understand space-time functionalism, or to understand space-time and emergent space-times more generally. Because if you wanted to be this kind of reductive functionalist about space-time, what you'd do is you'd pick out the role of the metric in general relativity, and then you'd look in your underlying theory of quantum gravity for something that realized the role of the metric. But if you found the thing that realized the metric in the underlying theory, what you would have proved is that space-time was in the underlying theory all along. If you find a feature of your spin networks that does exactly what the metric does in general relativity, then you've just shown that there is a space-time within quantum gravity in the first place. So you wouldn't have explained emergent space-time theories. You would have reduced general relativity to quantum gravity, which would be a great achievement. Don't get me wrong, but to say that this kind of functionalism is going to help with emergent space-times is just a misnomer. But, I mean, worse than that, of course, so it rules out the existence of non-spatio-temporal theories it works. But I also just think it's vanishingly unlikely to work for a theory like quantum gravity. I think if it doesn't work for a concept like temperature, the idea that it's going to work in this quantum gravitational concept, that you'll suddenly find neat identity relations between a notion at the general relativistic level and a notion at the quantum gravity level, is just a fool's errand. And within this framework, to be committed to the existence of, say, a space-time is to be committed to the existence of the realizer in the lower level theory. So if that fails, you're also committed to the fact that there was no space-time in the first place. We're just wrong. So now really are back to, Joan of Arc. It's just wrong that it's a bit hot in there. You're back to a kind of error theory if this system fails. So I think that's the wrong way to be a functionalist. I think the right way to be a functionalist goes back again to the late great Daniel Dennett. His ideas about functionalism, which David Wallace and I have called constitutive functionalism, which is an entirely made-up word by us. So it's not something you'll find overwhelming in the literature, but it's just a label for this kind of functionalism. So the thought behind that kind of functionalism is, look, forget about this functionalism isn't going to help you reduce theories. That's not what it's trying to do. It just tells you when a term applies, when you're correct to apply a term. And constitutive functionalism tells you that if a system is well modeled by, say, some belief desire psychology, or some space-time theory, and it contains a term, space-time, temperature, desire for wine, then that term applies. That's what it is to be. And when I say well-modeled, there's lots in being well-modeled. It's got to be predictive and explanatory and have all the good scientific values. So it's now just true that I want a glass of wine just in case attributing the desire and related psychology to me correctly models my behavior. In all the deep senses of correctly models, as I say, predicts it correctly, explains it, has the right kind of connections of predictions of other mental states, etc. The functionalism here is meant to legitimize the higher level ontology, the kind of the attribution of the desire, without any commitment to finding a realizer in the lower level theory. So on Dennett's view of how you think about mental states, it isn't that there has to be a particular brain state that corresponds to my desire to have a glass of wine. Of course, it's the case that somehow my brain has to model the belief desire psychology, like I am my brain. But it's not that there has to be some particular identifiable bit of neural stuff or neural state that corresponds to the desire. It's just that the whole system has to instantiate the psychology. So you don't need to find a brain state corresponding to a desire. So now, in the analogy with space-time, we want to say space-time functionalism says that space-time exists in a system just in case the system is well modeled by a theory that has structure that plays the space-time role. So if a theory is well modeled by general relativity, space-time exists for that system. Our cosmology is well modeled by general relativity. It's got a space-time. The solar system, well modeled by general relativity. There's space-time there. The metric field of general relativity plays the space-time role, so GR space-time exists. Now, it could be that you can reduce that somehow to the underlying theory of quantum gravity, but if you can't, that doesn't mean the space-time didn't exist in the first place. Your theory of quantum gravity had better explain how quantum gravity can model the same kinds of systems as general relativity. That's going to be the test for a theory of quantum gravity. But it doesn't have to do it by picking out something in the lower level theory that plays exactly the space-time role. It can do it in a more holistic sense. So if nothing in the fundamental theory plays exactly the role of space-time, then we say that space-time, general relativistic space-time is emergent. All right. So that's kind of the punchline. But I just want to point out there's this very annoying philosophical phrase. And once you get in the bad habit of using it, it turns out to be continuously relevant and kind of irritates my family. I can imagine being a philosopher's child. It's going to be awful. So one's modus ponens is another man's modus tollens just refers right to the fact that whenever you have an implicature, you can negate the consequent and flip it round. So I've been arguing that space-time is emergent, so constitutive space-time functionalism must be correct. I'll note that there'll be a whole load of philosophers that stomp their foot, accept that, if then, but say constitutive, that should be space-time, constitutive space-time functionalism is incorrect, so space-time can't be emergent. That's certainly a view in philosophy. You can always decide that this view that I've given is so implausible that we should get rid of these physics theories. But, if you're doing that on the back of the container metaphor, I think that's a very, very thin metaphor to try and deny this kind of possibility on the back of. And I think you need to bear in mind that our intuitions have been a very poor guide to new physics in the past. And so if the reason that you want to insist that this is all a terrible picture is because of a kind of intuitive container metaphor, I think that's a very bad reason to deny this kind of picture. Okay, so to sum up, there's an old idea about space-time that's based on the idea about space as a container, and it's appealing, but it's wrong. It can't accommodate the possibility of emergent space-time structure. It's also suspicious on its own terms. It starts to crumble under the weight that you put on it of interpretation. And functionalism about space-time might feel very surprising, might not feel intuitive, but I think it might have the virtue of being true. Right. Thank you very much.
Okay, we're going to have time for questions. So what we're going to do, if I can get this guy on. So folks with questions can raise your hand, and Josh is going to run a microphone over to folks with questions, and we'll take it away.
Hi. So I have two questions, if possible. One is, it seems that you were saying that like this container metaphor doesn't work because at the lower level, quantum gravity would negate the idea that we can think of these things being in space-time contained. But then you're also saying that space-time is really definable only where it's well described in GR, and until GR, this would be a curved container affected by matter, but still potentially a container, and in the framework in which we can define space-time.
Well, I think that so putting quite aside the issue of quantum gravity, I think there's a question about what you mean by in GR space-time as a container. So I was trying to pump that intuition, but I think what exactly does one mean by that, right? So part of what you might mean by that is, well, space-time's appropriately related to matter. But that's all captured in the functional definition, right? So the question is, that word container, is it playing a role beyond things that could be functionally specified? Or is the actual content of the container metaphor exhausted by the kinds of things that a piece of space-time structure can do? And if it is exhaustible, the container metaphor isn't adding anything and it's not a counterexample to functionalism. If it's not, then I sort of put it to people, it's very hard to explain what's missing once you've explained the functional role for space-time. Because rather clearly, the actual word container is a metaphor. So the question is there a way to specify the non-metaphorical content of kind of trying to give a non-functionally capturable view of space-time?
Okay, and so if I can give us, yes, just a second one and that's it. So it seems that you were saying in the slide that you still have a sort of realist view of functionalism, but also it seems that functionalism kind of would want to go into, at least as I see it, it goes into a direction that like sounds very instrumentalist in the sense like I just label a set of phenomena as one thing, and so it's a label more than I give than something that is really part of the essence or the ontology of the object.
Good. So David Papneau says I'm a semantic instrumentalist, and he's very often right. So there is something a little bit instrumentalist about this view, but it's not brute instrumentalism, and it is compatible with a kind of scientific realism, because I do take it that to be well modeled by a theory is a substantive claim. It doesn't just say that the theory gets the predictions correct.
Okay.
Right? So this is trying to piggyback on a notion that the theory is managing to specify genuine structural relations in some sense within a system. And then the words that we choose to attach to that are going to depend on, the way that we actually kind of attach meaning to the words isn't going to be by some kind of primitive reference or intuitive notion. But there is meant to be a kind of scientific realism in there that goes beyond the purely instrumental.
Okay, thank you.
Do you want to turn the lights up, by the way?
Wow, daylight.
Hello. Oh. So you've convinced me on how to think about space-time, but I'm wondering, is there any consensus in the scientific community about how it's defined? And if not, when you read like physics literature, how on earth do you understand anything?
Good. So, I mean, questions like what do you call space-time in a new theory are just not the kinds of questions that physicists explicitly ask. So this is not the kind of thing that could be a consensus about. I mean, there's plenty of consensus to talk about space-time structure and general relativity in a certain kind of way. I think, one of the things that first got me thinking about these issues were cases of bits of physics where I thought the physicists had gone badly wrong in the things they were saying about space-time structure. So they were insisting, so there's sort of sets of theories where they would say, like I've just postulated a flat space-time structure, where that structure wasn't playing any of the kinds of roles that the metric does in general relativity. And so I think that there are certainly lots of claims that get made about space-time in the physics literature, with, of course, just because they're busy doing like the important business of physics, without the kind of meta-analysis of what the basis of those claims for, or why, what the content of the claim that this bit of structure of space-time is taken to be. And I think that one of the benefits of this view is that you can get a bit clearer on some interpretational questions that get quite muddled in the physics literature precisely because the meta question isn't the kind of thing that physicists ask.
Thank you. I guess one more thing then. You talked about string theory in the beginning. Do you think string theorists agree with you? And do they believe in 10-dimensional space-time, the way that you've defined it?
I've never asked string theorists. I was using that as a kind of nice example of something that they 100% do in popular presentations of their work. I mean, my suspicion is that if I pushed back on the idea that it's really space-time, the vast majority of string theorists would very quickly back off that claim. But that's not based on my experience with string theorists. That's based on a very general fact that I found with physicists, which when you push them on what seems like an interpretation or a realist claim, they're often very happy to very quickly back off into some kind of more neutral position rather than defend it. And so it's, I'm never quite sure how one gets a handle on, I think the only real way to get a handle on what physicists think is to get quite deep into how they're actually using terms in their work, because I think as soon as you move them into kind of philosophical mode, they say things that seem slightly at odds with their behavior. I mean, most of them will become scientific anti-realists in like 10 seconds if you push them. But, you know, that's not really how they behave in the lab. So I think, yeah, so I don't know about string theory. It'd be interesting to, I've never done the kind of, I should talk to somebody who spent more time deep in the weeds of reading about string theory and talking to string theory about how, to what extent they really talk. They really talk amongst themselves in this way that they tend to talk when they put their kind of public-facing, what's string theory all about face on. I don't know how seriously they take those claims.
Hi, I kind of had a question that related a little bit to that, or kind of more to that. Should these questions be left to philosophers or to scientists? Or is there like a vital bridge that should be between them, kind of like we're doing now, this connection of not just maybe in space-time, but like in other fields of science as well, of maybe questioning things, not to the point of not doing their work, but are these kind of questions important? Because I would think that it would be.
So yes, I think the questions are important. Yes, they have to be done in concert between scientists and philosophers. I mean, there's space for division of labor, right? I think, you know, I don't blame a working physicist for not trying to do the philosophy of physics all the time. I think, I mean, maybe I should say why I think these questions matter. So I really do think, I think that sort of heuristically and in the development of new theories, these kinds of ideas can matter enormously. Now, historically, philosophical motivations have been very important, but I think more than that, I mean, very often, you know, physicists have doubts about a research program for reasons that boil down perhaps to conceptual or intuitive ideas that they have. And so you'll get ideas about what's a fruitful or a good research program, particularly in something like quantum gravity, where you can't base it on empirical results. People are going with gut feel. And when people are going with gut feel, they're probably going with something like implicit philosophical intuition. And so the work of making those intuitions explicit and actually understanding how they stand up to scrutiny, I think is the work of working out what's a kind of viable, coherent heuristic for moving on with a theory. So I do think that these, you know, whether or not you think, so if you think the fundamental theory has to have something that looks like space-time in it, you're really going to theorize in a very different way from how you're going to theorize if you don't think it needs to. So I think that the answers matter hugely for how theoretical physics progresses.
Hi, thanks so much for your talk. I thought it was really, really fascinating. And please bear with me, this is kind of a left field kind of question, right? So I was really curious about the role that functionalism is playing in scientific theories and things. I think it's really fascinating. And I was wondering if some of the same types of criticisms of functionalism that you find in like the philosophy of mind kind of map onto this type of scientific functionalism. And part of the reason I'm asking that is because we're borrowing a lot of terms from the philosophy of mind, right? So we're borrowing emergence, the hard problem, you know, those were originally like, you know, the mind emerges from, you know, physical matter, or the hard problem of consciousness, or, you know, things like that. Functionalism was also a term that was used like that. And I was wondering if there's like a scientific analog to those types of criticisms of functionalism, and if so, what would those types of things be?
Well, it depends which criticism of functionalism, right? So the hard problem of consciousness is the problem of what its likeness. And I mean, as I said, I think that it's very hard to replicate that problem. I mean, we were talking about this the other day, that actually somebody sort of tried, but I find it's very hard to, there's a very particular qualitative experience qualitative quality to experience that means that we have a problem for consciousness that is very hard to replicate elsewhere in science. I think some people think that the kind of whatever's left of the container metaphor that they can't quite express is meant to be something like the problem of qualia. But again, it's very, very hard. Because I don't share that intuition, it's extremely hard to get a handle on it, whereas it's not hard to get a handle on qualia. So I think that's one set of, I think the obvious thing to say is that that's one set of objection that just doesn't apply in scientific contexts. There are other worries you can have about how much you can functionally specify at once, whether if you functionalize all the terms in your theory, you haven't actually done enough to specify and pin down mental states or theoretical terms, and those will carry over. So some will carry over. Very explicitly, this is the Donetian functionalism is borrowed from the philosophy of mind directly. So it is meant to be analogous. It's just that I would have thought that it should be less problematic for science than it is for mind.
Should I go? Thanks again for, a really fascinating talk. Thanks for delivering it to the public. I think the danger of giving a public lecture is then you have someone like me from the public who's going to ask a question that is maybe off the wall, but I'm going to try anyways. And so I'm wondering, to what extent, if at all, would an idealist metaphysics address this question of what space is? If I'm Bishop Berkeley and space is the mind of God, or maybe space is in the mind of God, or space-time is the mind of God, does that make a difference?
I'm just not quite sure what Berkeley thinks physics is doing. I'm not enough of a Berkeley scholar. Is there a bit about... So Kant, like Berkeley, thinks that, I think has more developed views on space and time of an idealist nature than Berkeley, right? And he thinks that they're affected, the form of the space-time that we in fact experience is contributed by our own cognitive structure, if you like, if that's an acceptable way to express Kant's view, right? So that's going to apply to the space and time of our kind of lived experience, if you will. I don't know what Kant, and of course Kant thinks and then it's necessarily Euclidean and all these things that don't turn out to be true in these kinds of structures. So I don't really know what Kant would say in response to the kinds of layers of theorizing we're getting into, where a series of inferences can lead you to conclude that, contra to perhaps what you might think you experience, space is not really Euclidean, for example. So of course, if Kant's response to that is none of that is possible, then all of this is just irrelevant, and this physics is being ruled out by fiat. But you might want to think that there's something fundamental. So one thought that has something related to Kant, I suppose, is that you might want to think that the space and time of our experience and space-time as a theoretical construct are very different things and deserve a different treatment. And then you might have parallel debates about notions of space and time as they apply in our experience, and whether you should be a functionalist about those or how you should think about them. David Chalmers has a kind of space and time functionalism that is a functionalism very explicitly about our experienced notions of space and time, which is sort of, in a sense, disconnected from this in a sort of similar but parallel debate.
All right, hello. I'm coming at this from a pretty layman angle, I guess, but kind of what I got out of this was any kind of theory of everything or something downstream of all of it, functionalism would basically mean that there would have to be one small part of that, no matter how small, that explains space-time and kind of what we can measure. There can be all this stuff a part of it that we can never measure or understand, but if there's one part we can eventually get to that is explained from this upstream theory, then we can only use the downstream things we can observe to prove it. Does that make any sense?
I think it makes sense. So I think one thing that I was hoping not to persuade you of in that is that there'll be some small part of the fundamental theory, or I don't think there will be a fundamental theory, but the underlying theory, the theory of quantum gravity, there'll be some part of it that will explain space-time. Because I think one of the things that we tend to learn is that theories do have to explain why the higher level theories, perhaps the theories that came before them or that we have a lot of evidence for, they do a new or a broader or a more fundamental theory needs to explain why those theories work. That's part of its job. But it doesn't have to do that in a piece-by-piece way where one part of this theory explains this part of this theory and the other part of this theory explains this part of this theory. It can do it in a way such that it explains under a kind of regime and some modeling approximations exactly how some systems could behave in the way of general relativity. So the picture here is that if there is a theory of quantum gravity, it will ultimately be judged by its ability to account for general relativity. If it doesn't do that, it won't have done the job. That's what everyone's trying to do with a quantum theory of gravity. But it might do that in a way that doesn't say that space-time and general relativity is this bit of the quantum gravitational theory. It might do so in a way such that a big modeling context in the quantum gravity shows that you can have a GR system come out of it without a kind of term-by-term reduction.
Okay. Yeah, that helped a lot. Thank you.
Correct me if I've grossly misunderstood anything, but the gist that I got about constitutive fundamentalism is that it serves more of a defining role than an explanatory role in the things it's applied to. And I don't think I was convinced on how constitutive fundamentalism can prove anything new, or if it's doing any work, or if it's not just explaining the abstracta of what, the constitutive functionalism actually is. So can you use constitutive functionalism to reason something new, or do you need the abstracta to be prior to the functionalist theory, or can you use it on a new thing?
Okay, so maybe I should say what I think constitutive functionalism does and what it does not do. Maybe that's the most helpful thing to say. So what it's trying to do is tell you under what circumstances certain kinds of terms apply to the world, right? So it's saying, when can you talk about space-time and make true claims of the world, effectively? So it's a view on under what circumstances you can do that. There are other views. It's not the only one. So what's it trying to explain? Well, one thing it might explain is a kind of how possibly question. So how could there possibly be space-time in a world with no fundamental non-space-time? Well, here's a story about how there could be anything in a world where we haven't reached the fundamental level yet. Here's a story about what it is for there to be temperatures, genes, desires for a glass of wine. Now we can evaluate that story on its own terms, but it's a story about what we mean by saying that those things exist in the world. It's a perhaps slightly more metaphysically light, a version of what it is for those things to be in the world than one might have envisaged. But it therefore answers questions that how could this kind of view be compatible with a view of a fundamental reality that looks very, very different. So that's what I take it to be doing. Can it be applied to a new theory? Yeah, it's a view on how we think about theoretical terms. So it can be applied anywhere there's a theoretical term, so to any theory. So of course it can be applied to a new theory. It's not going to magically make you think something completely different about your theory, because it's an attitude to terms in your theory that is intended to, it's perhaps a counterbalance if you were being kind of a primitivist about some things in your theory, and it might make you think that more things are compatible than you thought were. And I think it has all kinds of, I think space-time functionalism has all kinds of consequences for how we think about individual theories. So I think there's lots and lots of work that a very specific view about the space-time role can do when we actually apply it to theories. Because it can, for example, show that two things are really notational variants of each other and shouldn't be interpreted differently. So it can do work in those kinds of contexts. Does that help?
Hi, my name is Arna. I'm a freshman, and I really enjoyed this talk. And I think as someone who's kind of new to college level academia, I'm still kind of trying to find my place within this big area we call our world. And I guess this might be a simple question, and forgive me if you've covered this already because I came in late. But what made you enter this so specific niche of philosophy, and what even, I guess, beckoned this concept of you challenging the fundamentalist idea that everyone has operated with before, or even looking at a different perspective?
so I mean, there's two questions, like, how did I get into philosophy of physics? And I mean, this was covered by Josh's introduction, but not, I mean, not, but it's okay that you missed that. I mean, it's wonderful, but, it wasn't exactly covered in the talk. So, I mean, I kind of fell in, I think lots of people somehow fall into their academic fields, and I just, in the UK, they make you choose a degree program before you apply. Not, and so I didn't want to do, I wanted to do physics, but I kind of didn't want to give up essay writing and reading, so I decided to study physics and philosophy, because it was a real degree program that existed. And I happened to go to a place where there were brilliant philosophers of physics, and then I realized that lots of the things I liked about physics were actually the philosophy of physics. And so that's a very classic path into philosophy of physics. You realize that the bits of physics you're super fascinated by are the things that they're going to let you study in the philosophy department more than in the physics department. This particular niche, I mean, there's kind of interesting question about how anyone does research in philosophy. Like whenever I'm sure all philosophers get this, right? When you, like, I'm on sabbatical at the moment, and everyone's like, oh, you're not working for 6 months. And I'm like, no, I'm doing research. And they're like, what the hell does research in philosophy look like? And you're like, oh, God, well, I guess it kind of just involves reading and thinking. I don't know. But what is it really? What happens? Well, you absorb a whole load of other people's ideas, and you find problems with them, and you find connections between them. And then, over time, you start thinking, oh, there's something here, and a new idea that has something in common with this idea and something in common with that idea. So like one potted version of why I'm a space-time functionalist is that one of my PhD supervisors was interested in functionalism, and the other one was interested in views on space-time. And I spent lots of time trying to make the two things they thought compatible. Kind of came up with this view, which I think is, those kinds of stories are how a lot of kind of new, if it could be called new philosophy, gets developed.
Yeah, we're going to do one more question, and then we'll go to the reception.
Awesome. I'll try to keep it short. Thank you so much for the talk. It's super interesting, especially someone who doesn't really do anything in philosophy of physics. But I wanted to ask a little more about the container metaphor. So my understanding, at least, is that the container metaphor, especially with thinking about space-time as container, sort of is insufficient in communicating and getting right the underlying theory of physics. So I'm wondering if the problem is with the container metaphor itself or with metaphor as a whole in terms of communicating physics. And so I'm wondering if there's space or there's a role for metaphor in communicating space-time functionalism. And hopefully that question makes sense.
Good. So I think there's definitely a role for metaphor in communicating physics. I mean, I think you very often can't do it without it. I think most of the time, the real process of coming to understand physics involves, a bunch of kind of linguistic and metaphorical description, and then learning a bunch of maths and learning how to apply it, and then working quite hard on applying it. And then eventually, you don't really need the metaphors anymore because you've kind of got the innate practice of what you do with these bits of maths, and you kind of understand how they work. So it's often a kind of step on the way to learning about something. And then I think it's only problematic, and I think it has a really important role to play in that. I think that one of the problems is sometimes we end up putting a lot of weight on metaphor in our metaphysical picture of what physics is offering us. And one has to be, whenever one introduces a diagram, like, whenever you're doing space-time, you introduce a diagram on a two-dimensional page. You've got to be really aware about what you're trying to represent, what kind of veridical aspects of the world you're trying to represent, and which things you're distorting. And metaphors are the same. They allow you to get across certain notions, and I think the container metaphor has bits of what I think of as the functional definition of space-time kind of baked into it. But then you've also got to bear in mind where your kind of representation or metaphor doesn't accurately represent the world. Yeah, I mean, I think there's a particular question that I've been interested in when I've been looking at lots of different physics theories, not just general relativity theories, which is about how one identifies space-time structure within a new theoretical context. So that's a little bit different for an undergrad course in GR, and I think there are cases where people go right and wrong in kind of interesting ways, but I mean, that will be in the details of how you... Well, there are lots of, I mean, there's a very large philosophy of general relativity, and there are hundreds of fascinating philosophical questions about general relativity, and I don't pretend to have touched on all of them in this talk. And I'm sure we can talk later about what questions do you think but I mean, certainly people do work on singularities and philosophy of black holes, that's totally a thing. What's beyond the singularity, I think it's a bad question, but I could tell you why. But anyway, I wouldn't, don't pretend that a single talk on space-time functionalism is the philosophy of general relativity, because I have lots of colleagues who would be devastated to think I'd given that impression. I'm certainly not.
Instead of cutting off this discussion, actually what I want to do is invite everybody to come upstairs to the Walker Ames room, where we'll have drinks and food, and please join me in thanking Professor Knox again for the lovely talk.